How's it going, everyone? Welcome to the 8th drill for the semester. Today we're going to be talking about fitting two-parameter models, and we'll do some transformations. We'll talk about some effect sizes, R squared, confidence intervals, and a real simple plot at the end. First thing, I wanted to throw out this reminder just on like naming things. I want to remind you that whenever you see things like M1, M2, mod 1, mod 2, mod augmented, whatever like that, think about, well, first of all, I just wanted to make sure that you're aware that like all of these, you can name these models whatever you want, but just have some way of naming them. So you'll see that as we go through today, like I use .mc to mean centered something or another. Sometimes I'll use compact versus augmented. Sometimes instead of calling it the augmented, if I'm making a model that the predictor is concerned, I might call it mod concern versus mod whatever other variable would go here to in a separate model if I was looking at multiple models. So just think about giving meaningful names, because if it is just M1, M2, for instance, it might not be clear once you have multiple models that you're looking, whether it's like across like homework or like just in your own stuff when you're looking through a bunch of different models in your own data. If you just have a bunch of things called M1, M2, M3, M4, M5, remembering which is going to be difficult. So just think about what you choose to name things, but you'll see how I name things anyway. So we're going to read in this data, and I guess I forgot I hadn't loaded my libraries yet. So again, this week it's just the tidyverse and LM support libraries, and we read in this data file, and if we take a glance at it, this looks awfully familiar, and you might think that this is the same data file that we've been using, but when we look at our describe, we can actually see that now our condition, whereas before the condition was a constant, now we can see that the minimum is 0 and the maximum is 1. And if you look back at the previous thing, you'll see that the names have changed a little bit, that now it's all lowercase, separated by periods, which is my naming convention, meaning I've already cleaned up this data and made it the way I like it for this particular data set. And but so this is one of the reasons that it's always important, and even when we haven't spent a lot of time talking about it, I've always put in the top of the script, whenever you read in a data set, you always take a glimpse and then always like look at your descriptives at least. Like that's when it says to like read in and explore your data, that's saying, hey, read it, take a glimpse to look at what variables you have, how many observations you have, is that what you are expecting. Look at the descriptives, make sure does everything make sense, what are your mins and maxes. If it's a 1 to 7 scale but your max is 77, then somebody had a typo, so that's why it's important to always do that initial quick exploration, take a glimpse at that data whenever you do read it in. So again, today this data set is actually a little bit different, that it has different conditions, but other than that, it's the same stuff as far as there are these 4 concern scores, and then 3 IAT scores at a baseline, a week 4 and a week 8. So today we're going to be asking a question: does concern score explain variance in week 4 IAT scores? So at some point we're going to have to compute some sort of composite, some single concern score, since we have 4 concern scores. But that's the question that we're going to be asking today. Does concern score explain variance in week 4 IAT scores? So what is our independent variable and our dependent variable in this situation, or the predictor and the outcome? I will try to do a better job of using the different terms that you might hear for things and making clear that, like, some people will call things the independent variable, but like in the general linear model, it's a predictor. So I use the terms predictors and outcome variables, but you can think of this conceptually as the independent variable and the dependent variable, or any other number of things that you might hear them called. So our predictor in this case is our concern score. We want to know, does that explain variance in some outcome? And what is that outcome? That outcome is the week 4 IAT scores. So we just want to know that by the time they've like 4 weeks after their baseline, does the extent to which that the participants express concern about something predict their IAT scores, their implicit bias, supposedly. So what models do we compare to test this hypothesis? Well, our compact model is going to be an intercept-only model. So we have BO, which is the intercept, plus error. Or more concretely, our outcome, our week 4 IAT score, we are predicting with just the intercept plus some error. In the compact model, and then in the augmented model, we're having BO plus B1 times X plus E, or in other words, we're adding in that slope of the concern score. So our week 4 IAT score, we're predicting the intercept plus the slope of the concern times that participant's individual concern score plus some error. So our compact model, the only difference is it's an intercept only model. And then in our augmented model, our 2-parameter model, our 2 parameters are the intercept plus the slope of their concern score. So we simply take the intercept, we take the participant's concern score, multiply it times some B1, whatever B1 is, we're going to multiply that by their participant's concern score, add the intercept, add some error, and that's what their week 4 score is. So all of this will become more and more concrete as we work through this over and over. So first thing that we need to do is we need to compute this concern score as a composite score of our predictor. So we're just going to take the mean of these 4 concern scores, and first thing that we're going to do is check to see if there are any missing values, because if we have 4 concern scores and say somebody's missing 3 of them, do we really want to take the average of just that one item? Or if they only have 2, if they're missing half of the items, you know, if they're missing too much, we might want to make their concern score NA and leave them out instead of computing that average. So all I'm doing here is taking the bias data frame, and I select those 4 scores, and then pipe that into is.na to test are those NA or not. And so that's just going to be for each value, like is it NA, true or false. And but you can see that here, sure, it's only 78 rows and 4 columns, but you can imagine if we had a dozen columns and 10,000 participants, that, you know, we don't want to have to sit here and scroll through and look through tens or hundreds of thousands of trues and falses. So now just take this output and pipe it into table, and it will output to tell us all 312 things are false. So there are no values that are NA in this data set. If there were, then it would say, you know, true 1, false 311, or whatever the case may be here. So none of them are missing, so we can go ahead and just take the means of each of these rows. So when we come here and we see you know, concern 1, 2, 3, and 4, we want to take the mean of these 4 of this row. We want to compute a mean, and then we want to take these 4 in this row and compute a mean, and that's where we're going to use this row means function. Now I do have a note here that normally you would want to do some form of reliability, like checking Cronbach's alpha or something, depending on what your measure is and what's normative in you know, your field of research. But that's, you know, a topic for a different at least drill or lecture, possibly a different class, depending on how much Bill wants to get into it or not. And you know, if you have questions about it, feel free to ask me offline, or I'm sure if you went to Bill with questions about that specifically, he'd be happy to answer, but we're not going to actually cover it. We're just going to say magically we know that these are reliable, and so we're simply going to compute that mean. So now something that I want to be sure to point out as far as like how to type this out, and how it makes sense. One of the great things about pipes is that pipes can be used inside functions as well. So in other words, all we're doing is we're going to take that bias data set, and like I said, we select those 4 columns, and then we pipe that into this row means function, and all it does is it outputs the mean of each row of whatever gets put into it. So here it just computes those row means for each of our 78 participants. So once I get that row means chunk of code written, all I do is then take that and cut and paste to put it into wherever I want it. So in terms of how I got this, I take my bias data frame and I want to mutate to create a new variable. That new variable is called concern, and it equals, and then I literally just paste in that what I just did, that bias pipe chain. Bias to select those 4 columns and then take the row means is what the concern variable is. And now when I run just that chunk of code, it gives me that concern. And so then I go back, throw in my assignment arrow and reassign it to bias, and now when I look in my bias data set, I have that concern score that is just the average of each of the 4 concern scores for each participant. So the whole point of this last little thing that I did was just to show you, like, in terms of when it's not pre-written code, like how do you easily get all this in there. Like basically I'm saying to write the code first, run it, look at your console, make sure that it's outputting what you want, then copy and paste that into your mutate, and once you get that working, it's a bad habit. I see people who will try to store things without running it first. So basically what I'm trying to get through here is make sure that you run this and that this is outputting what you're expecting before adding in your assignment arrows. Don't get in the habit of then saying like, all right, so now we're going to create this other variable. So I'm going to add in bias and then pipe into mutate, whatever equals blah, 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 and assigning over that bias data frame on the first try before running just this chunk to figure out, oh wait, that doesn't work, something went wrong here. So it's bad form to start with and to work with the assignment operators in your stuff. Get the code to work first and then go back and add in your assignment operator at the end. Anyway, point is that we now have this concern score that's just the mean of the 4 items for each participant. So now that's this new variable that we have. So now we can go ahead and begin fitting our model. So we're going to fit our 1 parameter model and our 2 parameter model. So our 1 parameter model is just we use the LM function and we tell it our data equals bias, our bias data set, and we want IAT week 4 regressed on the intercept. So regressed on that 1, but just again to remind you, that is not regressed on 1, that means regressed on the intercept. And so that's going to be our mod.compact, or that compact model. Our 2 parameter model, mod.augmented, we tell LM that the data is bias. We want IAT week 4 scores regressed on the intercept plus concern, which is that variable that we just created here. So we want our second parameter to be a slope for that concern variable, and that's going to be our augmented model. Now one thing I point out here is that as far as R goes, anytime you have multiple parameters in the model, you can leave off the intercept. You don't have to actually put this 1 plus. So here where we have week 4 IAT regressed on 1 plus concern, or the intercept plus the slope of concern, if you just put IAT week 4 regressed on the slope of concern, R actually reads those the same way. It will automatically put in the intercept when you have any sort of slopes in there. It assumes that you also want the intercept. If you want to leave off the intercept, you would actually have to explicitly leave it off by telling it, 0 plus the concern, or like leave off the intercept, but I want the slope of concern. That's not what we're doing, though. So point is, for today and here at the beginning, like, I will be including the 1 plus just to make it a little bit more concrete visually, that this is a 2-parameter model. You have your intercept plus your slope of this other variable. So this is also a 2-parameter model because it's, even though it looks like it's just the slope of concern, it also implicitly has puts in the intercept, and if you run it, the coefficients actually does give you 2 parameters there, the intercept plus that slope of concern. As we move on, I will get away from including the 1 plus stuff just because it's unnecessary to put it there. But like I said, for now, I'll leave it there just to make things clear. All right, so now we fit our compact and augmented models. So now let's check out our models. We're going to look at our model summaries. So when we look at our compact model summary, T equals F. This is basically what we've been looking at before. So we know then that this estimate here, our intercept, is the mean of the outcome variable when everything else in the model is 0. Well, there's nothing else in this model, therefore this 0.4172 is just the mean of the week 4 IAT scores. And this we'll come back into what this F test here is testing and what this p-value is testing, but it gives us our sum squared errors at 12.9, degrees of freedom, etc. When we look at our model summary for our augmented model, we now have something new that we haven't seen before, because we now have this extra line here below the intercept where we have another estimate, standard error F and P. Well, so what this is telling us is now our intercept, our predictions are that intercept, which is our BO, plus B1 times the concern score. So in other words, here is our B1. The slope estimate for, or the slope for concern is our estimate here. And so if our intercept is 0.6985, then our prediction is going to be 0.6985 times negative 0.049 or 0.4094 times whatever that participant's concern score is. So what we're predicting, pick any given participant, take whatever their concern score is. If their concern score is 5, multiply 5 times this number, add it to that intercept, and that is that participant's predicted week 4 IAT score. However far off that is from the actual score will be its residuals and be that error, but our prediction is their concern score times this slope, this estimate, plus this intercept. So R is giving us model comparisons here in each line. So what models are actually being tested in these model summaries? So here, in other words, what is this F here testing? You might think that well, what's being tested here is the intercept only versus the null model. But you'd be wrong, because it's not comparing the intercept only model against a null model. It's actually comparing a model that includes everything in the table except for that line. And so, like, we'll use this term focal parameter. And so in any given thing, whatever our focal parameter is just the individual parameter that we're focusing on. So here, this F test, if our focal parameter is the intercept, this F test is testing what is the difference in error between whether or not this intercept, this focal parameter, is included in the model. So in other words, if we manually do this as a model comparison, it will be a model that has the slope of concern but no intercept, compared against a model with the slope of concern but also including the intercept. So if we run the model comparison manually by specifying a model without the intercept and one with the intercept, but both having the slope of concern, we can see that we get that same f-stat that our model summary puts out. So when we look at model summary here, a point that I'm trying to make here is that this model summary does not test the intercept only model against, or because the model summary of the compact model does test the intercept only model versus the null model here with this f test. But once we get into a 2-parameter model, this f is not testing the intercept only versus the null. It is testing a model that has concern and the intercept against a model that has concern but no intercept. Here on this line, this f test and this p-value is testing, okay, well, if concern is our focal parameter. So now we're just worried about this line in our summary. And so if we take this parameter, this concern, in and out of the model, that's what we're comparing. So now we're comparing an intercept-only model versus a model that's the intercept and this slope of concern. So if we manually do this model comparison, that's where we get this f value and this p value from in our model summary. It is just comparing, basically doing a t-test, comparing that intercept only model versus intercept plus the slope of concern. And what it's comparing is that error. How much is error being reduced with just that change of adding this one parameter in there? And in this case, we can see that it's not significant. So there's not a significant effect of this parameter, the slope of concern. So in both cases, R is comparing the model to a model that contains all of the parameters except for that focal parameter, the focal parameter being whatever the parameter is on the line that you're interpreting. So here, this f test is comparing with this focal parameter of the intercept. Take that in, leave that, or put that in, take that out. Like, is there a significant reduction of error there between those two models? This f test here is, well, if our focal parameter is concern, this concern score, if we put that in and take it out and compare those two models, is there a significant reduction in error? And the answer is no, there's not a significant reduction in error when we include this concern score. So what does this p-value really tell us? The p-value is the probability of obtaining this f statistic here, or a more extreme one, so getting an f bigger than 2.329, in a random sample of 78 from the population, if the null hypothesis is true. So if it's true that the null hypothesis, that concern has no effect, if that is true, and we randomly sample 78 people, and we do it again and again and again, as we randomly sample sizes of 78, there is a 13% chance that we could get this difference that we get, even if there's not really an effect. So there's a 13% chance that we just got this effect, or a difference this big, just by chance, if the null hypothesis is actually true. So if we look at our coefficients of our compact and augmented model, though, like, why does this intercept change? Why, if our intercept only model, if that's the mean of our week 4 IAT scores, why are we not getting that as our intercept once we put in that slope for our concern score? And the answer is because we didn't mean center our predictor. Because our prediction line has a slope now, that it's not just predicting that straight line across at whatever the mean of y is. It doesn't cross the y-axis at the mean anymore. It's where y crosses at 0. So we'll come back to this and get a lot more concrete with it here in just a few minutes. But first, to look at our confidence intervals for this, we have our confidence interval for the intercept would be 0.32 to 1.08, and then the confidence interval for our slope is negative 0.09 to 0.012. And so you might hear the expression, if the 95% interval captures 0. In this case, it does, and that's why this is not significant. Anytime the 95% interval captures 0, then it's not significant, because remember that our confidence intervals are not about the sample. Confidence intervals talks about the population. We believe that the true population parameter, we are 95% confident that the true population parameter falls within the 95% confidence interval. So in this case, our 95% confidence interval is negative, we'll call it negative 0.09 to 0.01. So we are 95% confident that the true population, that the effect of concern score, that the true slope is between negative 0.09 and and 0.1, which means 0 is in there. So we cannot say with confidence that the effect of concern is not 0, because, well, 0 falls in that parameter. So the actual true parameter of the actual true slope of this value might actually be 0, even though on average it was a negative slope of negative 0.04. So for effect sizes, I just have a note here that I type, R2, but I mean R squared, and I just want to make it explicitly clear that that means R squared and not R2. And it's just easier to type R2 than like R, up to. So that's what I go with. But anyway, so let's compute, we're going to calculate R squared for that slope of concern. So here's our confidence interval, here's our estimate, and if we go back to look at our model summary right here, we want to compute R squared for this slope of concern. So we have our compact model, and if we just use, a couple weeks ago I pointed out that you could call, the dollar sign like residuals or fitted values, all those sorts of things that are stored inside the model. So if we call those residuals and then square those residuals, and so here inside the sum function, all I'm doing is squaring the residuals for each participant's prediction, and then if you wrap that in sum, basically what you're doing is you are getting the sum of squared residuals, and that is the sum of squared residuals for SSE for the the sum of squared errors, which is the residuals. So that is the sum of squared errors for the compact model, and then the sum of squared errors for the augmented model. And now using the formula that we know with sum of squared errors for the compact model minus the sum of squared errors for the augmented model over the sum of squared errors for the compact model gives us 0.0297. If we go back to the model effect sizes that we used last week, we can see that our delta R squared is 0.0297. So what that tells us, because R squared represents the percentage of variance that's accounted for by some particular variable. But in model effect sizes, it's the dr squared, the delta R squared, which means delta means change. So delta R squared is just the change of R squared. So in other words, if we look at what the R squared, the percentage of explained variance in our model is, just how the model comparison looks at how much is the model, how much error is reduced comparing the compact versus augmented model. So with and without this concern score, how much error is there? This delta R squared is how much does R squared change when we put this in. Like, we know that it's going to that we will explain more variance, or at least at a minimum it will not get worse. It cannot get worse. It will get better. How much did it get better? Well, including this concern score explained about 3% extra of the variance. So if we take this concern score out, we have 3% extra of unexplained variance. When we put it in, we explain 3% extra of the variance. So then, earlier I said something about mean centering. So we're going to go back and look at this augmented model again. Look at our summary, and we talked about how our intercept. I've been saying this already. I've been planting this seed for like 3 weeks now, maybe even 4, and putting it even up at the top of the script these last few weeks, just to really try to hammer this point in. That the intercept is the mean when everything else, when all the other predictors are 0. So this intercept is the predicted value, that it's the mean when everything else is 0, meaning when the concern score is 0. So this is the average week 4 IAT score for people who have a concern score of 0. Then this number, our slope, tells us how much we expect that estimate to change each time the concern score changes by 1 unit. So if this goes up from 0 to 1, we expect a negative 0.041, we'll round, change in the outcome. So we expect, as the concern score goes up, the week 4 IAT score will go down by 0.041. If it goes up by another point, it should go down again. So in other words, where somebody's concern score is 0, we predict 0.699 as their week 4 IAT score. If a participant has a concern score of 1, we simply go down by 0.041. So we would predict 0.658 as their week 4 IAT score. Somebody who has a concern score of 2 will go down, an additional 0.41 to be, 0.617. Concern score of 3 would be 0.535, etc. So all we're doing is we're multiplying their concern score by this slope, and then adding that to the 0.699, that estimate. But when we look at our scores, we see that the minimum concern score is 2.5 and the maximum is 10. So there are no 0s, 1s, or 2s in our data. So, like, we're talking about the average of somebody whose concern score is 0, but we literally don't have anybody with a concern score of 0. So that's not, meaningful that, for a score that doesn't exist. And furthermore, like, the actual mean of our week 4 IAT scores is 0.417, and that's not what our intercept is. But if we mean center our variables, then that changes. So here, all I'm doing is I'm subtracting the mean concern, which is 0.417, from each concern score, and I'm creating a variable called concern.mc. I use .mc to mean concern, mean centered. So we take our bias data frame, pipe it into mutate to create concern.mc, which is the difference between the participant's concern score and the average. And so now, if I look at the mean of that variable that I just created, it doesn't say 0, but it's a really, 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 really small number. And the only reason that it's not exactly 0 is because of rounding issues. So anytime you see something like this, where it's like something times 10 to the negative 16th or something crazy like that, it's 0. So anyway, Now the average, or 0, is the average concern score in our sample. So now if we take this and plug this mean-centered concern score into our thing, so this is the same model as before, only difference is instead of using regressing IAT week 4 scores on the intercept plus concern, it's the intercept plus concern mean-centered. And so now let's take a look at our two models, and we can see that nothing changes for the slope of our concern variable. The slope is still the same, but you can see that our intercepts are different now. And now with the mean-centered concern, our intercept is actually the mean of our outcome variable, because now the intercept is the mean where everything else is 0. Well, where is this 0? This is 0 for the average participant. So this is the average IAT score for the average participant, but still the slope reads as, but for every 1 unit increase in concern, we expect the prediction to go down by 0.041. But in this case, somebody who has a 1 doesn't actually have a concern score of 1. They have a concern score 1 point higher than average, because average is 0. The last thing that I'll show you real quick, and just to reiterate, so here, notice that I didn't use t equals f in the model summary so that it actually reported those t-tests. So earlier, let's just hit up on this again. So here, as a reminder, this p-value here, what this now t-test, instead of before it was an f-test, and the real takeaway here is t is just a transformation of f. T is so a t-test and an f-test are really one and the same. What this t-test here is testing, and this p-value, is if we have a model that has everything in our model except this focal parameter. In this case, our focal parameter for this t-test is the intercept. So if we have a model that has everything except for this in it, and then compare that with the model of putting this in it, what is that t-test? What is the t-test on the reduction of error there is kind of how you can think of that. And is that significant? Like the t is 9.089, so yeah, p is a really tiny number. Then, with a focal parameter of our mean-centered concern score, if we put everything else in the model into a model, which means our intercept, and compare that against the model as that intercept plus our focal parameter, this concern score, what is the t there? Is that a significant difference? Is it a significant reduction of error for that one parameter change? And the answer is no, it's not a significant reduction in error. But again, that didn't change from what we ran earlier from the non-centered version. All that will change by centering things is that intercept. So when you mean center your predictors, you give your intercept a meaningful interpretation. Because it's otherwise, if it's not mean centered, then the interpretation is wherever this predictor equals 0. But when it's mean centered, 0 means the mean, and therefore it's the intercept is the average for the average of the other predictors. So we'll be seeing a lot of that as we move on, and that'll become more clear. So the last thing I want to show you here, just in these last couple minutes, is an example of a plot where we're going to add just a couple of things on to what we've done before. So if we start just by making ggplot and telling it like we have our bias data, and we give it aesthetics to tell it x is the mean-centered concern and y is our week 4 IAT scores. And all I did here was change it to color equals red, just because. If ever you're just wanting it to be a constant color, it's not an aesthetic. It is just, a defined argument. So you tell it color is red. If you want green, whatever, it doesn't matter. So that's what we have here. So something new, we're going to now add on another layer called geom smooth. And in geom smooth, we're going to tell it method equals LM, and that's telling it to, because if you there are other methods that we may talk about later this semester, or that you may have heard of, called like Loess lines and things like that. But what we want to tell it is we want it to use LM, and so that's telling it we want it to use a linear model to give us our prediction line and those 95% confidence intervals. So when all we have to do to get that this prediction line and our confidence intervals is tell it geom smooth and method equals LM, and then the last thing is I just add on theme classic just because that's my default. I like theme classic with the just a clean white background. So just to be absolutely clear, what we're looking at here with these confidence bands is you can imagine that if we look about at -2, right here is the score. This blue line represents the score that we would predict for anyone with a score of 2 points below the mean of the concerned scores. We would predict whatever this value is of the blue line. Somewhere it looks like slightly above half or 0.5 for their score. But then the 95% confidence interval at that value of 2 points below the center, below the mean, would be here between, I don't know, we'll call it 0.7 maybe, and, whatever this value is down here. So here in the middle of our data, we have more narrow bands, but as we get further out to the edges, that our confidence intervals get wider and wider. But anyway, so that's just a real simple scatter plot with confidence intervals. And that wraps up what we're going to be covering today. We will surely be in 2-parameter models here for a few weeks, both continuing with continuous things, then moving into dichotomous models. And so we'll spend more time talking about all this, but hopefully this at least gets you started on thinking about 2-parameter models. And if you have any questions, as always, let me know, and I will see you all on Thursday or Friday.